in any event, I thought we've been talking the last couple of days about some of the work that has been ongoing in the United States. And one of the most recent things is what we call the development of PRS or QRSS specifications. And what these represent, it's a growing trend in the United States to have construction specifications, to have contractor performance, to have contractor bonus and penalties geared to the actual performance of the pavement that is built. So what I'll show you is a little bit of what work has been done here over the last years to develop what we call the QRSS. Now, when I do this, I think the most interest is the fact that in the development of the QRSS, we've had to take the MEPDG, which is the Advanced Computer Program Code that was developed for the United States and is their current design procedure, and develop closed-form solutions or very quick solutions that we can put on microcomputers to generate the system. And I think this will be the most important and most interesting part relative to the work that I'll be presenting. I happen to give this paper, I'm a member of actually a National Academy Science panel that is being funded. This project that I made the presentation on is, if you're familiar with the Strategic Highway Research Program 2, it is one of the research programs. It's about a $2 billion study involved with the development of performance-related specifications. So with that in mind, I gave a little talk and about a week ago, 2 weeks ago, and what I'll do is try to quickly go through the talk for you. So if you have any questions at any time, please feel free to ask. I don't want to make this very long. Okay, this is being funded, the work on the PRS development under itself, an NCHRP, which stands for the National Cooperative Highway Research Program. In the event you don't know what this program is about, is that in the United States, every state in AASHTO ballots on what they think are the most significant research studies that the country should undertake. And if there is 2/3 of the consensus, in other words, if there are 30 or more states that feel the same problem should be worked on, the United States government will dedicate funds and ask people to bid on proposals for this project. So the NCHRP stands for National Cooperative Highway Research Program. I'm sure you've seen a lot of their reports and used them. What's important here is that the study development of the PRS actually linked together a lot of other projects that were developed in the United States. In fact, I put here that it really links together about 15 plus years of major research in the country. And I've had the fortune or misfortune of being the principal investigator on almost all these projects. So it deals with the 919, which goes back to the development of the super pave system. The 137A and the 140B are the projects that developed the MEPDG for the United States and AASHTO. The 933 is one that we did to develop and integrate mixed design, asphalt mixed design into the MEPDG. And what it really represents is the culmination and the input of structural design into asphalt mixed design. And this is the first time this has been done in the United States. The ability to integrate mixed properties into the structural performance of a road system, and that becomes important. By the way, I'll tell you that there are comparable studies being done in the concrete area. In other words, what's being developed are PRS specifications for concrete or rigid pavement, and they are being developed from the MEPDG model for the concrete and into concrete mix design and construction characteristics. So I'll talk to you only about the asphalt part. Okay, as we're talking about here, the asphalt mix is linked to the MEPDG and it's linked into the structural design. The whole purpose of this is to really come up with what we call a rational set of performance specifications for road and highway construction. Okay, as I've indicated, that really what we're doing on the left-hand side is there are studies that related, the sharp studies related to the enhancement of asphalt mix procedures, studies over here that were intended to develop in the enhancement of mechanistic structural design procedures. And what they have been done is to merge these in the 922 technology to come up with a probabilistic performance-related specification. I'll show you in just a moment. I won't get into a lot of details, but this is not only a mechanistic-based, fundamental asphalt mix design, but it relies heavily upon probabilistic solutions and analysis into looking at pay factors. Okay, I've told you some of this before, but if we just start looking at the MEPDG, because we're going to be looking at variability of the constructed product, if I were to look at how long it would take in the MEPDG computer solution, if I were to do a complete Monte Carlo simulation, for example, 6 variables, only 6 variables, that it would take me 32 computational hours to arrive at one full probabilistic Monte Carlo solution using input standard deviations or variances of only 6 variables. In the MEPDG, there happen to be 64 variables for just asphalt pavement. So if I wanted to do with the MEPDG a full-blown probabilistic analysis of the MEPDG to arrive at some probability or performance-related cost specifications, it would only take you approximately 10 times e to the power of 18 computational hours to do that. Or putting it this way, it only takes you about a gajillion years to do one little problem. So immediately the problems that became evident to everybody is that while the MEPDG is a very powerful tool, that it is probably not the best thing in the world to use and try to build stochastic processes and reliability directly into it. Okay? There is reliability in the design guide, but you see it circumvents everything because it just says I am going to guess what my reliability is and variance of my final predicted variable. What we're really talking about is that every one of my variables that are the dependent variables, I need to be able to input in the variance. I need to know what is the variance of the asphalt chemical. What's the variance of the thickness of the layers? What's the variance of the air voids in place? All of these things. You see, and if we were to do that, it's physically impossible to do. So what was the solution that we turned to? Okay, it was obvious that even Monte Carlo simulation on relatively quick laptops that were in existence 3 or 4 years ago. And yeah, we have improved the speed over the last couple years, but maybe instead of 10 to the 10th years, we're now at 10 to the 8th years. It's still a physical impossibility. So we came to the quick conclusion that this is not possible. So what did we take the alternative? What we had to do here is to see if we couldn't take a matrix of runs of all the key variables in the MEPDG. And then from that, try to develop some accurate statistical closed form predictive equation. In other words, if we come up with a simple closed form equation solution that predicts fatigue, or predicts rutting, or thermal cracking, that would be fun. After we found that, what we're going to do here is get into looking at a spreadsheet solution that really makes the assessment here of what is my job mix compared to the actual plant mix. When we talk about pay factors, specification, quality control, quality assurance, this is the concept that we apply anywhere in the world. I have a design that the engineer does. I'm going to pay a contractor to place that design and to do it as close as he can to the design job mix formula. What we have to incorporate is differences between what the contractor places and the variation that he may have in doing that. Okay, what we have here then is to start incorporating probabilistic procedures. I don't know in your approach for specifications if you have what we call PWL or percent within limits or probabilistic. In other words, you sample 10 times and you see what percentage is. Well, that's the very first cursory step when we get into probabilistic analysis. I will show you basically here where we have used now very powerful statistical approaches in terms of not only Monte Carlo simulation, but getting into Taylor series as well as Rosenblum to try and determine variances of multivariable equations. After this is all done, to come up with some type of user-friendly computer program that could be used. So that was the attack that we took about 6-7 years ago, that we're going to run a lot of MEPDG programs, try to get closed form simulation solutions, and that's what we have successfully done over the last 6 or 7 years. And that's where it's of interest to you folks into some of the closed form solutions that we do use. Okay, there are limitations in the closed form solution that I want everybody to be aware of. Okay, the limitations are, unlike the MEPDG that we developed to incorporate a complete range of axial load traffic spectra, we do not do this in the PRS. So we're still using the old easels, which most of the world is still using in terms of the design tools. Okay, we do not have any seasonal changes for unsaturated E, although that can be easily incorporated into the program. Okay, we use as the primary indicator of how good or how bad a project is, something I want you to look at, which we call the PLD. And it really represents the service life difference between the job mix design and the field mix. So we reduce everything to two things. One, I want to design something for X years. Number two, I want to build something that I think wants to last X years. The trouble is the contractor is not going to always meet X years. He may have X plus an increment of life. And if he does that, he's giving us a product a little bit better than we asked for. And as a result, as an agency, we may want to give him a little bonus, which in the United States we do. Not every state will give a bonus, but some states do. Typically, the maximum construction bonus you would get would be something in the ballpark of 8 or 9%. So if a contractor does a dang-up job, he may be awarded 108% of his contract value. On the other extreme, if we want to design something for 20 years and it lasts what the contractor builds, it's going to last 8 years. Okay, he's cheating us to 12 years of the life of the road. So by God, he's going to pay for it. He's going to pay for it either by getting 70, 80% of what his bid price was, or if it's real bad, the agency's going to make him take out what he put in and replace it so that it does that. But again, we'll be coming up to this as the PLD is a very important parameter in this. And I want you to be thinking of what the contractor bills minus what the design engineer thinks he wants that thing to last. And that's going to be the key parameter in what we're going to do here. So the PLD is really the difference. It's the basis for awarding penalty or bonuses to the contractor. Okay, again, like I said before, this is very heavy statistically. We use very advanced statistical studies, far above and beyond use of typical normal probability equations. So it is a very high-intensive statistical model that's been generated. Okay, like I said before, the predicted life difference is very simple. Okay, and you, again, just start thinking of this concept. You know, I'm going to design something that I think is going to last 20 years. Just because I want to have it designed for 20 years doesn't mean when we build it on the road, it is going to last 20 years. That's the contractor's quality, and that's why we do quality control and quality assurance of the product that we're putting in. Okay, how do we calculate the variance with the service life? To make things short, we'll do up to 1,000 Monte Carlo simulations. It's a brute force approach that takes into account the actual variance of every key variable that will define the performance of the road. Where do I get this information from? One of two ways. If I'm talking about the job mix formula, what the design is, we can go to your historic construction records. I am sure Costa Rica has a catalog for every one of their projects, and somebody should do this, or maybe you've done it already. You should be able to tell me for the last 10 years, every asphalt project that was done, what was the variance associated with the job mix formula that was constructed on the road? You should be able to tell me what is going to be the statistical variance of the percent passing a number 200 on your construction project. So you have this information available. If you don't have it available, there are national and historic variances. In fact, if you go to 1975 textbook that I like a lot, I forgot the name of it, but you'll find a whole summary of historic statistical construction variances on every one of your volumetric properties that you do. So the thing is, with the job mix design, we can use historic, historic variabilities, historic standard deviation, historic variances associated with each one of the variables. You guys should be able to dig that out if you do not have it. Okay? What do we use for variability of as the constructor or the contractor constructs the product? Well, we're no different than the way we typically break. We'll take a project, if it's 100,000 tons, we'll break it up into what we call statistical lots. And a lot is whatever you want to conveniently define as a lot. In the agency, it may be 1 day's production of a hot mix plant, or it may be 2,000 tons production. But what you're going to do is take a lot, and you're going to sub that up into statistical sampling areas we call sublots. And you're going to sample each one of these sublots. And as I sample asphalt content 4 or 5 times in a lot, what I do is get the true estimate of variance of what the contractor is producing. If he is exceptionally good at doing a very good uniform control on his product, he should have a standard deviation of asphalt content that's no greater or maybe even less than your national historic average. But if he's real poor and is not controlling his product very well, his variance of asphalt content in a lot may be 2 times the magnitude of your historic variance. So to summarize, if we're talking job mix, we use national historic variances or statistical variability. when we go to the as-built product, we use the variability that the contractor is actually producing statistically in a series of sublots, and we estimate the variance by each one of the lots. Okay? Okay, like I said before, the as-built variances, the key specific things. You see, all of these are what is used in the PRS model, and this is another key thing to see. Okay, what you're going to be interested in is the mixed volume metrics. The variability of the asphalt content, the variability of the air voids in place, the variability of the gradation, how much your binder is changing during the construction process. Okay, you're going to be looking at how much the field density changes, and you're going to be looking at, is the contractor, if I'm calling for a 3-inch layer of asphalt, is he giving me 3 inches, 3.4, or is every day he's giving me 2.8 so he can make money? So these are things that we're interested in, even in today's specifications. Okay? What's important is that these are the same important inputs that are used in the PRS or the QRSS program. Because every one of these that you'll see, if you look at the predictive equation that's in the ASTRO design guide, you will see that every one of these is an important factor affecting the E-star value and the performance of the pavement. Again, I want you to start thinking of 2 parameters: job mix versus what the contractor does. I talked to you about this before, but what we're looking for the job mix, the variance or standard deviation we're going to use is going to be the historic literature for typical plant variability expected. You guys, again, like I tell you, I bet you have all this in records. Luis, do you have this summarized? Does anybody know?
Well, we have here a lot of data here, a lot. We have been doing this for 10 years, so we should have a lot of data.
Every country, every agency, every state collects this data. And I'm saying it's available. The next thing you should do is take this data and analyze it and see what your historic values are. Statistically, you can pool all the projects. In other words, if I have 20 projects over X years, I can take the individual standard deviations of asphalt content in every project. And statistically, I can pool the variances to come up with what is the best estimate for Costa Rica. So what I'm getting at is this information, either you have or you have the database for it. Okay, when we talk about here, the plant produced, okay, think about what the contractor is going to do. And the easiest thing to do is I want you to start thinking of these 2 functions as a demand function. The demand is what we're using for design. What we build is what the capacity of that system is. I want to design for 20 years. This is the demand I'm putting on my road. The contractor is going to construct it, and it's going to be what the true capacity of that road is. Unfortunately, it could be 10 years, 18 years, 26 and a half years. And that's what we have to find out. Okay? As we start getting into how this thing works, again, we're not using deterministic solution, we're using a probabilistic solution. So that in reality here, I have, if I were to look at design life and my cumulative frequency distribution, what we have is that on a 50, or the mean percentage is I may want to choose 20 years. But because I cannot uniformly design and construct, I'm going to have some variability, which is reflected by the slope of that particular curve. If I were to take the integral of the CFD, I would get my typical bell-shaped distribution. So we're going to have one for my design mix, and then we're going to have what the contractor puts in. And just look at this. Design life in years. Again, this magnitude, if the contractor gives me this curve, he's giving me more life than what I as a designer wanted. So as a result, should I give him a little bonus or not penalize him? That's the agency's decision. On the other hand, if he puts down a bad mix, puts too much asphalt in it, doesn't compact it enough, uses a thinner section than what he should be placing, what he's doing is in reality decreasing the life of the road. So that when I subtract this from this, again, what I place minus what I thought I had, my design, the as-built minus my design, if this number is positive, I'm in good shape. If it's negative, the contractor's in bad shape. Okay, so that's the simple concept of what we're doing. Okay, I'll quickly show you, and I just want you to leave with an understanding. It probably took myself and the team probably about a year and a half of simulations of the MEPDG and all kind of fancy statistical modeling to come up with a very close form solution. What you have here is this happens to show the correlation for rutting in the asphalt by, quote, the closed form solution that's in the QRSS versus if we use the rutting in the MEPDG 25-minute solution using cumulative damage. So the net result of the simplified equations that we came up with, here is the correlation between them. I apologize because this thing, the R squared adjusted, was 0.996. I could never get 1.0 on it. Okay. Some of these correlations were done on thousands of simulations. For fatigue, I think it pushed 8,000 simulations. So these are very quick, comprehensive, like I've been telling Lewis, this work you're looking at about really 6 to 8 years and about $6 million of investment in research. Okay, it was very extensive. Here's the correlation. This happens to be for rutting in the asphalt. The next one will show you what the correlation for fatigue cracking look like. Again, this is taking the MEPDG, if you're familiar with that, the complex, multi-temperature, multi-stiffness, multi-everything. Every 2 weeks we take a signature of the changes of the modulus. We do cumulative damage. This thing here is a simple equation which reduces everything to what we call effective temperature and effective modulus. And it's strictly very good. This one here was a little bit better, 0.998. And then, of course, we did very poorly on the thermal fracture. I could never get this last 9 out here. But the point I'm making is that we've taken the MEPDG in all its complexity and all the time and the solution it is, and developed 3 sets of closed form solutions that you can put on this computer program. I could input the ASTRO input and in nanoseconds get thousands of solutions. So that's basically where we are with this one. So, the Monte Carlo simulation part of things, we have built this into the program. I don't know why you can't see everything on it, but here's a plot of the number of samples that we'll do. We triggered this initially in the program that we ran. This happens to be on the dynamic modulus. Okay, you input in the mean value and the variances associated with asphalt content, air voids, bitumen volume, gradation effect, the 4 variables I have in the predicted model, the viscosity, and what you'll get here is in the blink of an eye. When you touch this thing, it'll start at the beginning and go to the end. And what you're seeing then is the mean value and the standard deviation and the variance of your analysis. So the power of the closed form solution is extremely critical. So it'll give you the idea of or what we did now to cut back on time. If you see, you go beyond 300, 400 simulations, it levels off. So instead of it taking a nanosecond, we've reduced it to a half a nanosecond for the solution. I'm just joking. Okay, I don't expect anybody, I don't know how familiar you are statistically, but I said this before. The program that is developed uses extremely powerful solutions from probabilistic viewpoint. I am not a big believer in normal probability applied to highway procedure. The reason is that, you know, if I use normal probability, it's possible for me to get a negative percent passing another 200. Or it's possible for me to get 50,000 feet of fatigue cracking in the pavement per mile. So all of these things, because the normal probability is what? Continuous from minus infinity to positive infinity. I always have problems with my extreme values. So once I go beyond 95, 90, 95%, I'm really in danger of getting, oh, I'm following the statistical equation, but I'm losing track of reality. Most of the equations and analysis that are used, I basically think the most powerful distribution in the world for what we use is the beta distribution. And the beta distribution has a mean and the standard deviation of variance. It's computed exactly the same way. The only difference is that there is a B value and an A value, which are limits that you put on that my distribution will never be less than and will never be greater than. So if I wanted to look at asphalt content, I'm going to put an A here equal to maybe 0% or 1%, which means I can never get an asphalt content to be 0 or to be a minus 2% asphalt. On the other hand, the B value here is something that will be the maximum. And if you know, for example, how we do distress in the MEPDG and the design guide, you see the percent crack frequency that I generate, the distress that I generate, represents the amount of fatigue cracking I have in both wheel paths. Okay? It represents the amount of cracking in both wheel paths per mile. So what is the maximum value of the cracking percentage that I can have in the MEPDT? It's going to be 2 times 5,280. I cannot never go above 10,560. We have the same limit that we apply for thermal cracking. So you see, I could never do this in normal probability distribution, but we put limits on with cracking and I can control the minimum and maximum. Anyway, these are the equations that you would use. Very simple to implement. I'll show you the power of this because this happens to be for thermal cracking. We put limits on here. This is the A value of 0. I don't have a limit of a negative thermal cracking, but I put my A to be 0. And if I come out here with Ray Roque at Florida, when he developed the thermal cracking module, he developed it as a completely failure condition where I would have cracking at 12 or 15 feet so that I could never have across the lane width, so that I would never ever be able to predict more than 2,100 feet per mile of thermal cracking. So again, this is advantages of the beta distribution that are programmed into the PRS. Okay, another very, very critical concept that's going to have direct applicability is what we use, is the introduction of what we call effective temperature. There's effective temperatures for fatigue cracking, effective temperatures for permanent deformation of the AC. What does it represent? When we do the MEPDG, we do up to 70, I don't know if you realize this, we'll do, in a typical design life, we'll do maybe 70 to 80,000 stress shots and strain shots of the pavement every 2 weeks at a variety of locations in the XY plane and Z plane. And we're going to be changing modulus due to seasonal effects, temperature effects. We'll do 70,000 changes in the modulus to come up with the damage. Okay, what the effective, simple concept does here is I'm going to ask myself, if I were to do the MEPDG project or program, what would be the one effective temperature for a given design site, okay, and a given pavement structure? That would give me exactly the same answer. That's critical to understand. I'm going to replace my master curve and all the different seasonal effects I have, whether I'm in Canada or Costa Rica, and I'm going to come up with a way that would say, if I were using the simple approach, for example, in Costa Rica for rutting, what would be the one simple effective temperature that I would use to compute the E value? This has been solved in the QRSS. Again, I showed this equation. I don't want you to memorize it or copy it down. But in the program, you see these things are very simple, straightforward. They physically utilize the frequency of the vehicle speed. It will use the thickness. The Z value represents the thickness of my pavement. It starts giving you the mean annual, all the climatic conditions that are very simple that you get without the need to have first order weather stations. You should be able to take the country of Costa Rica and tell me what is the inches of rain or millimeters of rain throughout the entire region of Costa Rica. How much does the mean annual air temperature vary by month? All these things are quick and dirty estimates of climatic information that are readily available if you have. You no longer have to have 20 years of hourly climatic data that you need to do the energy. So this greatly reduces the amount of effort. So I use these equations, come up with an effective temperature. What do I do then? I go to my master curve on the E, and with the effective temperature I can tell what is going to be my effective E, my effective modulus that I should use in the MEPDG. And that's going to be used in the 3 closed form equations that we have. So again, this I call a poor man's approach, but it's very accurate. Okay, if you look at what we have, typical results, let's say for rutting. You see, we've had effective temperature results for rutting for many 70, 80 years. The first one I'll call your attention to is the sky right here. What's the temperature? It's 140 degrees. Okay, where did that come from? Well, when Mr. Marshall, Bruce Marshall, developed the Marshall stability test, he said that the critical temperature I want to evaluate this thing is at 140 degrees. And since Bruce Marshall's day to even today, states that use the Marshall, you typically will do it at 140 degrees Fahrenheit. So for all practical purposes, Canada uses a Marshall stability done at 140 degrees. Phoenix will use a Marshall stability at 140 degrees over here. The government of Qatar uses Marshall stability, and they're at 160, 170 degrees. Everybody uses that as my effective temperature. A couple of years ago during the SHARP program, a fellow by the name of Carl Monosmith came up with his own version of the effective temperatures for the earth. What you see here are essentially the 4 curves that are developed from the MEPDG and the effective temperature. And it gives you an idea of what value you should have depending upon the traffic conditions that you have for running. What's the mean annual air temperature in Costa Rica? Anybody know?
Something to say?
It's a homework problem.
1780.
Let's say it is going to be 80 degrees. Or maybe higher.
Yeah,
80.
around.
Okay. So what you'd be saying here on these four relationships, their frequency, which means how fast or how quick the traffic is moving. And here at 80 degrees, you can see that my effective temperature may be as high as 150 to 150. This is 147. This is like 155. This may be 135. And what happens here is that the slower the traffic moves, okay, if you look at the frequency effect here, if I have an interstate highway or a high-traveled highway, I'm going to be, because my stress pulse is so quick, that I'm going to have an effective temperature maybe a little bit less than 140. So the point is that you can go through and map all of Costa Rica and develop, depending upon the thickness of your pavement system and the speed of your anticipated traffic, if you're at an intersection, okay, you're going to be at very low frequencies, and you're going to require a little bit stronger. Okay. So this is how this thing is used. They're also developed here for fatigue. It's the same concept. And again, these things were literally not done overnight. These took months and months and months of work. They're reasonably excellent. They're, again, you have, like I said, this one's based on almost 8,000 units. So it's a simple equation that essentially you can physically utilize. And again, it's intended to be, I don't have to do a master curve, and I don't have to take the master curve and put it into a cumulative damage plan. It's real quick and dirty to the point. This part of what I'm talking about you can use as an initial design procedure from what's been developed in QRSS. Okay, let me talk to you a little bit about the project input and how we have it for the agency. The agency will select whatever you feel appropriate, and you do that in order to give you payment. Okay? Here you have a plot of predicted life difference. If it's 0, I'm good. And I might want to give the contractor here is 100%. I may want to give him 110, 108% bonus. Okay, when it comes down to over here, if he's less than this value, I may want him to replace it. In the procedure, we do not tell you what to use. This is, every agency has their own control over the nodal points that they physically use to define their payment, penalty, and bonus. The thing is, for every one of them, here's the case that is used by one of the states. But it gives you an idea of how I can either penalize or award the contractor for doing better than the mixed design or poorer than the mixed design. Does everybody start seeing the concept that's involved in it? And it makes so much sense, you know. That's why probably nobody will ever use it. Okay, here's the cost analysis that's here. I don't even want to try to explain this to you in a short period of time. But you see, in the design guide, we have the capability to do 3 different asphalt layers. I could do a surface course, an intermediate or a minor course, and then a base course. So if I want to incorporate cost, penalty or cost associated with all 3 of them together, I can go ahead and do that. I also have, I want you to notice that what we have here these are associated with running distress. If I cross the border here, this part is associated with F. So this stands for fatigue cracking. This stands for T sub F, it's thermal fracture. This part over here, if you can't see it, is basically for IRI. So what you have the capability of is to reward or penalize the contractor for the following distresses. If he does a poor job at running, if he does a poor job with getting a mix that's going to crack, if he does a poor job in selecting his binder content and binder type for thermal fracture, and if he does a very rough job to begin with. What becomes important here is these little beta factors. They represent the agency's attitude as to what percentage I want to put on running distress, what amount of money I want to penalize or reward the guy if he gives me a good cracking pavement, and here for thermal cracking. Now I want to ask you, see, I want to pick on somebody not to embarrass you, but I want to see how smart you really are. What would you use if I said you have a pavement with running, fatigue cracking, and thermal cracking? And keep in mind that beta factors have to add up to be 100%. What percentage would you put for running? What percentage would you put for fatigue cracking? And what percentage would you put for thermal cracking?
I would go for a 0 with the thermal fracture. And
What are you going to use here? What would you use in Costa Rica?
0.
Okay, good.
Then
Anybody that's in a hot area, you probably would use 0. I don't care the mix with thermal cracking because it's probably going to be 0 anyway. Now you have the question between fatigue cracking and
probably it would depend on the binder that I'm using, but right here we're having more problems with the fatigue than with the rotting. So I would probably do like a 60-40.
64. Any other ones? You're a learned, educated. What would you?
No, I agree with Jose Pablo. Maybe it would depend on the region that you are.
Well, you see, for one thing, there's a couple of things I want to leave you with. It's a very difficult decision. However, what you want to look at is down the road. What I want to be sure is, the way I look at the world, is that after 20 years, I would much rather have a pavement that doesn't have a crack in it, that may be badly rutted, because my rehabilitation is simple. It's milled and filled 15 or 20 years from now. If I start destroying the structural integrity of the pavement, what that means is that in my rehabilitation, I am probably going to have to remove the thing and build another one. So in that line, you may want to put more emphasis on making sure that the pavement is really not going to crack and not get structurally degraded due to fatigue damage compared to the idea of doing running. But again, we don't recommend in the program what to do. What we recommend is say is every agency is on their own in selecting the beta factors. And you have to go through that argument, and discussion. Okay. So, again, that's the way the total benefit is. Okay, this is the important slide. It kind of tells you here now, let's get into the simple performance test procedure. And if we look at the prediction models, trust me that what you have is the most important simple pavement performance test that we found, and what this is based on is the E star of your asphalt mix. That is by critical, the most important variable that drives running performance, thermal fracture, and fatigue cracking. Once I get into fatigue cracking, I have another factor, which is the structural capacity of the pavement, thickness of the asphalt, and a few other things. But what becomes important here is that the dynamic analysis and the dynamic modulus is the critical, simple performance test variable, if I had to pick one, that governs the performance of an asphalt pavement. That's why Luis and your lab is placing so much emphasis on the E-Star device. Okay? And that's what becomes important. In the PRS, there are two ways in which I can get the E-Star value. The first way, if you're familiar with the predictive equation, I take the volumetrics of my mix and I can input it into what we call the Witczack predictive equation. I happen to know this guy pretty good. And what you can do is generate the master curve just based on the pure volumetrics of the mix. So that's one way I can solve this. The other way I can do it, and it's obviously the best, but it's the one that's going to take the longest to implement, is the fact that I can actually do the laboratory test, the E-Star test, in the laboratory. So that what we're saying now is, number one, the E-Star test is by far the most important. How do I get that? I can do it one of two ways. I can measure asphalt content, air void, gradation, plug it into the predictive equation, go into the QRSS and do a design and see the life. Or I can actually take my effective temperature, the effective frequency, and go to the laboratory and measure the E-Star value at this one critical point and compare it to the E-Star minimum that we would need in the design process. So that's what is being pursued. Okay. You know what, I'll probably leave you if you want a copy of this, so you don't have to copy all the equations. But this is what we're about, the development of the E-Star master curve. Okay, this is what I'm here for. That's what you're looking at, the best way to test the result, get a master curve, characterize it by sigmoidal parameters, and et cetera. And then what you're going to do is come and get the effective temperature and frequency by use of the equations that I have. Here's one for rutting. Here's the one I showed you for fatigue. I generate the effective temperature, effective frequency, and I can generate the effective modulus. Okay? So once I do that, what I'm going to do is go to my master curve, and I will find for Costa Rica in the southern part of San Jose on a given design project that what I'm going to have here is this is going to be my effective E that I'm going to use. Okay, let me skip the software here and get to a couple comparisons. Okay, what we've done in the latest project is we've actually sampled 3 field projects in the United States. One is in Rhode Island, northeastern United States. One is in Texas. I don't know if any of you know where that's at. Another one in Utah. So we've taken 3 actual field projects and sent all the materials. We need raw materials to do the job mix formula master curve. And then as the contractor pays in a given day, we'll take material for 4 sublots for every lot or every day that he does it. So what we're doing is having enough material here on 3 projects to do a job mix master curve as well as the effective E's to check and validate the system. Here are the cross sections of the pavement. They're probably going to mean too much to you. I'll show you the first slide is this, for example, represented in Rhode Island, the different material types. I'll call to your attention here that we did have the Utah and the Texas had rapid, which complicates things a little bit, but it did have recycled material. Here was the 76 grade, and then we had some 64 grade. The Texas material, unfortunately, had a little weightless. And I say unfortunately because immediately that should put on a red light or a red flag to using the predictive equation. Okay, you probably have seen a lot of these in your lab, but this is the technique we did. Exactly the technique you follow now is what we do and everybody does. To generate here the laboratory blood, core the specimens, and get them used to doing. Here's our E-star chamber, and this is the indirect instrument. We also did creep compliance tests for the load element. So that's what we were doing in terms of this thing. I think you guys have used the procedure that we developed at ASU, and it's to get a technique to when I manufacture plant mix to a certain air voids, I have to know how much material I have to put in the mold together. And the way we typically do it is what we call the mask to air voids. We'll take basically here a high air voids, a low air voids, measure the modulus by trial and error, assume there's a linear relationship. So if, and this is done, I use sublot, so that what I'll then do is that if I know the actual distribution of air voids in a sublot, I can then predict the distribution of E within a sublot or a log. And that's the process that's done. Okay, here are some results. I just want you to get thinking about this. Here, for example, is Texas. Here's what the contractor performed in lots. One was for fatigue and one was for asphalt. This is the master curve, and it shows me this is what the designer said the E should be. So immediately looking at this diagram, what do I conclude about the Texas thing? Did the contractor give me something that was better or poorer than the other? You have two guesses. 50% probability of saying you're right. Now, obviously, this is the fundamental thing you want to look at. You see, this is in my job mix. I want to have that value. What the designer said I should have. If what the contractor is giving me is this, if he's below the line, that means he's giving me less quality, which means that he is going to have a negative predictive life difference, which means he should be punished. On the other hand, if there are any points that lie above here, he's on the good side. Okay, I just showed this as an example. Okay, here's an example of the data that was physically measured in the lab versus the predictive equation. Okay, so you would conclude the Witczak equation is totally horrendous and not doing it good. Is this still here today? Okay, if you did, please walk out the door. Remember I told you that this particular mix used in Texas, in Rhode Island and the Circus was an SPS mix. And the SPX is a polymer modified asphalt. There is absolutely very little, if any, data of polymer modified asphalts that was used in the 4,000 points that I used to develop the predictive model. So therefore, everywhere I go, I say, do not use the predictive equation to predict the modulus of polymer modified asphalt. And what this clearly does, it re-emphasizes the finding of what I've been saying. So if you have polymer modified asphalt, you can do this and get the comparison and see what it is. But you see, for the one surface mix, which was SPS modified, But you see, when I look at all the other mixes that were used, the Rhode Island based, the non-modified mixes, and look at the measure to the Witczack predictive equation, that they're not there. And this is, again, the type of information we'll try and generate here. But what you see is for all of the master field points that were generated, that you get the feeling, well, what we're saying here is that I can use an equation based upon mixed volumetrics, and I'll get about the same value of E star that I would if I measured the E star. Okay? Now that works two ways. To start with, what we're promoting is that every agency start using mixed volumetrics to generate what the minimum E star value is. However, with time, we'd like to see E star become, and that's what the work that's been done on the simplified asphalt performance analyzer is about. To be able to just take it at one temperature and one frequency and just hammer it out like a Marshall test and do your QA/QC. Okay, here you can't see it real good, but what we have now are a series of plots of the three locations. If I were to predict fatigue cracking here from the laboratory measured values, okay, in other words, we actually ran E star at the effective temperature frequency. Here is the fatigue cracking that we would generate from the short-term solutions, the closed form solution of the NEPCG. And you can see that for all three of the locations, you get a very reasonable fit predicting. And all this says is that what we're claiming all the time is that I can use one or the other. I can use volumetrics or I can use SPT, physical testing at effective. And they work pretty good. Okay, this one was not so good. This represents the looking. And I'll tell you what we found. And I show this because it's obviously a problem or a bias in the running. But what this result did show us, and this was just analyzed here about a month and a half ago, that there were subtle differences in the computational techniques that are used in the computer program that uses the measured E compared to the NEPCG. So this problem can be easily corrected, will be corrected, but it just comes to show you that we're still on the drawing boards with this thing and got to do it fresh. However, everything else I'll quickly show you. You see, here is the plot if we have predicted life difference. Okay, again, it's not perfect, but again, look at whatever we're predicting by measuring the E compared to the volumetrics, they're pretty close to each other. So again, looking at this, you start getting a lot of reason to believe that this is a system that will work really good in three projects. We're in the process, the next and final step of this is we're going to try and get 14 field projects in the United States and really add to the database, and hopefully in a couple of years, you'll see this type of activity being implemented across the country. There's a table. The thing I'll show you here is, see here are the effective frequency and effective temperatures for each one of the mixes that we have. This is for running. This happens to be Rhode Island, Texas, and Utah. Here's the effective frequency and temperature. This is what we choose as the measured SPT from the effective temperature. So again, to make things simple, I would say if you were doing this test, you're going to use here a frequency of 10 hertz, and you would test the E star at 80 degrees Fahrenheit. So every one of your points that you would do, I don't do a master curve on every sublevel. I just take it and do it at a one test temperature. Get an E and compare it to what I showed you. So here's the summary of these things, and you can see they vary by temperature and location. I think there's just a few more slides. This shows you predicted life differences and coefficient of variation. This happens to be, for example, within a given lot. For example, lot number 1, 2, 3, 4, 5. Here represents the mean value and the standard deviation that was found. And from there, you do the statistical analysis. And again, I'll just finish up with the summary slides. I think the E-star comparison is very good to excellent. And again, the QRSS volumetric should not be based upon modified estimate. The running comparison I pointed out, I think that will be corrected in the next month or two. Fatigue cracking, thermal cracking, computer disincentive, basically penalty, bonus, predicted life differences, all these came out to be very excellent. So these are based on 3 field projects. Obviously, we want to do more. Again, 922 is the first year interaction of structural mixed design and the structural design. It's been really an enormous challenge to put this together. Again, I started working on this thing over 15 years, and I don't want anybody to think it's something I started 8 or 9 months ago, or the country has started 8 or 9 months ago. It's probably upwards to $20–25 million of research, 15 to 17 years of research. For example, when I led the team for the development of the LanammeUCR in the country, I had 30 people from around the world working on my team. So it's not even me. Really a lot, a big variety of people that have contributed. Okay, the most important thing you have to realize about this, and people say I don't believe it, the problem here is that you have to recognize the MEPDG has been field calibrated by hundreds of field sections in the United States. So what we're doing is comparing performance that we know we can do a pretty good job in predicting. We don't know how it'll be in Costa Rica yet. I'm sure you guys will find out. But in the United States, from the northern border with Canada to the southern border with Mexico, from the Atlantic Ocean to the Pacific Ocean, it works reasonably well. And we have national calibration factors that I can adjust for fatigue design, thermal fracture, running of the asphalt. I can do all these things very good. And as we try to do performance-related specifications, don't forget that that PRS has been field calibrated to a national mechanistic model that we have. Okay, I think it is the future conceptual methodology that has to be used if you're thinking of a rational, fundamental way to do performance specifications. The way we do specifications today is ludicrous. They're meaningless. They really are. We shouldn't even use specifications or use performance take factors on what we do now. For example, just to say that my asphalt content, it should be with a limit of plus or minus 0.3 tenths of asphalt. If it's 0.32% more, what is going to be the impact of that on performance? But yet we're going to penalize or make a contractor rip it out. In fact, if I use more asphalt and a lower layer of asphalt, am I decreasing or increasing the load? Looks like nobody knows the answer. I'll tell you, you're going to increase the load. Because what they're going to do is put more asphalt in the layer in which I'm going to be getting my extreme fatigue cracking. Okay, and as a result, the greater the bitumen volume I have, the less likely I am to fatigue that. So in practice today, we'll penalize somebody for putting in a little bit too much asphalt, but in reality, he might be extending the life of the road. And this is the difference between the empirical, judgmental take factors we have now compared to, let's look at what really happens to the life if I have this or that. And that's what this study has been doing. Okay, should it be implemented tomorrow? I absolutely not. I think the biggest thing we need to do is it's been under development enough. We poured enough money and time into the development of this. Yeah, there's a few wrinkles we gotta do in the bulk computer program. But in reality, what we need to do is say, I have a system, let's take it out in the field and see how good or how bad it works. And even when I say that, I'm not 100% confident that it's going to be the mecca and the solution there. However, what I'm convinced that what we do need is a research team can't be the ones that are going to decide this. We have to have a panel, which is what we're trying to do, of actual state DOT people, that this is their life, bituminous engineers, material engineers. We'll give them the results and let them make a decision 3 years from now on, yes, this can be implemented, no, it shouldn't be implemented, or yes, it may be implemented with the following changes. So what we're trying to do is collect hard field data and then give these to people that really run DOTs for them to make the final decision. So that's where we are right now in this, and I guess that will cover what I need to say. So I'll open it to any questions you may have. You want to switch on the light? Let me catch how many people are still sleeping. Oh. Okay. Anybody have any questions? Really did a good job. I know it's a lot. Okay. Throw the ball back to you.
I have a question. Initially, you mentioned that the random variables in the models, in the closed form solutions were normally discrete.
They could be any.
Yes, sir. But and then you say they're beta, or is the distress function in part of the beta distribution for the variable?
Yeah. When you get to, there are several steps in building models. For one thing to simulate, what you first of all do is get damage. Then you apply traffic, because that gives you the total damage over your design time. And you do the damage for fatigue. So I have one big area equation for fatigue damage. I have one big equation for permanent deformation damage. I can convert that now into design life. Okay? If I wanted something that's going to last 20 years for fatigue cracking, I can convert what we actually build or what we actually have, the structure, into whether it's going to be 25 years, 15 years, 12.5 years. So we develop, eventually the final equation is going to be in terms of the predicted design life. Then I have the predicted design life is going to be a function of all of these things. This pavement structure, the E of the asphalt, the location, the temperature. The E in turn is going to be a function of the airboys, asphalt. So what we then do is we simulate every variable, okay? And what we assume is, I want to get, what is the true variance of my predicted life distribution? That's what I'm after. Okay, we don't guess that. What we say is I'm going to use a combination of Taylor series, Rosenblum procedure, and take the variance of every one of my variables to calculate what the variance of my independent variable is. So that's what we do, and that's the hard part. What the AASHTO design guide does, it immediately puts a standard deviation on the WT18. That's what I want. But I don't put individual variances on the structural number, the layer coefficient, the thickness of every one of the layers. I don't do that. So this thing now is the most sophisticated way. In other words, I have okay, I have some mathematical function that says y is a function of n different variables in the equation. I make this as simple or complex as I want. What I'm ultimately after is I want to predict the y bar and I want to predict the variance of this. So what I really want to get is something that gives me, if I plot y, and this is the frequency distribution. What the Astro Design Guide says is this is WT18, and I assign a standard deviation to this guy. Okay, what we do, there are two ways to do it. I can really cut to him and say this is going to be the variance of y. In our case, y is the predicted life difference for fatigue or running or thermal fraction. Okay, the way that, the most accurate way to do that is that in essence, y bar is simply going to be what? The function of when I use the mean values, okay, of every one of these variables. And if I use Taylor series, for example, it's going to be my y squared total is going to be some function of variance of x1, variance of x2, and the variance of x3. So mathematically, we can model these by Taylor series or beta distribution or Rosenborg, for example, every one of the variables that I get. So I don't get the solution here for the predicted life. I'll take all of this and I will get a distribution of predicted life difference as a function of PLD. And what I'm going to generate is something that looks like this. In doing this, what I'm going to be doing is to use a beta distribution, okay, which is now defined by ABX. And that's really the power of what I have.
So the A and the B are predefined, I guess. The A and the B, the limits of the distribution
Yes,
are predefined.
Yeah, this is going to be bounded by the fact that, for example, if I have here the predicted life difference, what I'm going to have is I have limits as a part of this equation. Obviously, it's very complicated. However, within the y, what I'm going to do is I'm going to have, let's say, the damage that's associated with the PITRA. And you see, I'm going to generate something like this. I'm going to use here a beta distribution to define the damage by using a minimum and a maximum value when I do the Rosenwood or my Taylor series. So this is being taken into account in generating this thing. And that's how when I had the variance, to remember the one curve, I had the cumulative frequency distribution, which is taking this and integrating it. So this is at 50%, 100%. Remember, I had a curve that was something like this. Well, you see, this slope is in reality proportional to the variance of the line. If I had a big variance, this thing would go like this. If I had a very small variance, it's going to be almost infinite. So, again, it's a complicated process of the closed form solutions, but all of this has been done by first building closed form solution for predicting fatigue damage, then inverting that to find what is going to be than pure damage. Then what is gonna be the total damage by taking into account the actual traffic? Okay, and then once I have the total damage, to be able to calculate the predicted life difference. So that's the concept that's used. So every one of the variables that is used is treated as a stochastic variable.
So in the program you input the mean and the standard deviation.
Absolutely. Yeah, it's going to use basically, you'll generate a distribution curve for the job mix. You'll generate a job mix for the job mix formula. You're going to generate a distribution for what each lot that the contractor has. And that's where that long equation, cost equation came in. That really has to do with the amount of lots, percentage of lots that comply with the analysis. That's why there's a signal value. Again, the details are, it's very comprehensive, but it's something you have to